Okay, well, welcome to our first Thinking Beyond webinar, which was previously known as Ask a Physicist. We have updated the title to encompass a wider range of topics, but our format will remain the same with a presenter in the first half of the hour, and then we will get to questions in the second. But if you have a question at any point during the presentation, please use the Q&A feature at the bottom of your Zoom screen. This is being recorded and we will upload it to YouTube if you want to rewatch it or watch any of our previous Ask a Physicist webinars or share with anyone you think might be interested. Look for that later this week. Our next Thinking Beyond will be September 25th at the same time, 6 p.m. Mountain Standard. And we will have guest presenter Dr. Narosha Murugan, and she will give a talk on biomagnetism. Registration will open at mid-September, so look out for the emails and social media posts with the link for that. And with that, I will turn it over to our moderator and director of the Beyond Center, Paul Davies.
Thank you very much, Jessica, and welcome everybody to our revamped monthly series. We decided to change the title, rebrand it a bit, because we'd sort of run out of physics questions to ask and answer, and we felt that we wanted to cast the net a bit more broadly, but we will of course still be covering lots of physics topics, including this evening. And we thought it was very appropriate to have a talk by my esteemed colleague Maulik Parikh, who is an expert, world expert on black holes, because a lot of you will have seen the film Oppenheimer. And to a physicist, when you mention the name Oppenheimer, you tend not to think of the Manhattan Project, you think of his work on black holes. Well, Maulik will come on to that in a moment. I expect many of you have seen the film. My wife and I went on Saturday evening, and I very much enjoyed it. Of course, it's a 3-hour marathon. But I thought I'd just say a few words, because for me it was a special occasion. I knew, or at least met, some of the people portrayed in that film, and I just thought I'd tell you one or two personal stories before we move on to the more formal part of the evening. So among the people featured in the film, I did get to meet Heisenberg and Edward Teller, who comes across as a bit of a villain, and Richard Feynman, who is sort of relegated to the guy playing the bongos. I think he did rather more in practice. The person that didn't feature in the film, but really sort of loomed over the entire program, was John Wheeler, John Archibald Wheeler, who I knew over many years, knew him very well. And he and Niels Bohr worked out the quantum mechanics of nuclear fission in 1939 and sort of set the stage for the entire atomic bomb enterprise. But the other person who played a very significant role, who I met when he was in his 90s, was Mark Oliphant. He was an Australian theoretical physicist. He worked at the University of Birmingham in the UK, and he, in 1939, had recruited two Jewish emigre German physicists, Otto Frisch and Rudolf Parals. And they were working on nuclear physics. And in March of 1940, they sat down one evening and worked out what you would need as a critical mass of uranium to make a bomb. And they discovered that this was a feasible proposition, and they checked and rechecked their calculations, and they convened a meeting of the Royal Society in London. And this led to the establishment of the British program called Tube Alloys. That was the code name that Churchill chose. And it culminated a year later, that is in mid-1941, in something called the MAUD report, M-A-U-D. And that's a little bit humorous because Niels Bohr was trapped in Nazi Europe, and his colleagues in the West were sort of a bit concerned about his safety. But he did get a message to the British authorities, which said that he was perfectly safe, and tell Maud Ray Pent. And there was a lot of puzzlement that this was some deep code about nuclear physics. Anyway, they this tube alloys culminated in the thing called the Maud report, where the RAF flew Niels Bohr out of Europe. There's a short point in the film where he says that he passed out because of lack of oxygen, and this was true. He was in the bomb bay of a Mosquito bomber. And one of the first things he did when he landed was he said that he'd like to see his Aunt Maud, who lived in Kent. So hadn't been in code at all. It turned out that she was a governess that he had known over many years. But anyway, just to bring this to a conclusion, that the Maud report was sent to the United States. This was before the United States had come into the war. And the famous letter that Einstein and Szilard sent to Roosevelt led to the establishment of, a year before, of the Uranium Committee, but they did nothing. They basically were more interested in a reactor than a bomb. And in the UK, the scientists were very concerned that the Americans weren't taking it very seriously. So Mark Oliphant flew, and he told me this when I met him in his 90s. He said, well, they wouldn't trust Frisch and Parles because they were, German names. They thought, well, it'd be much better if an Australian went. And he did, and he went over to Washington and was astonished to find that the head of the Uranium Committee had just filed the Maud report in the safe and hadn't shown it to anybody. So Oliphant sort of thumped the desk and said, bomb, 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 rather than reactor, and finally came to the attention of Lawrence and Fermi, who then went to Vannevar Bush, who led to the setting up of the Manhattan Project. So Oliphant was the key figure there, and he subsequently became governor of South Australia, and I met him after he retired from that position when I was still living in Australia. So I thought people might be interested to know that backstory and some of the players who didn't make it to the film, but were important, I think, in the entire program. So I think you've heard enough from me about these personal reminiscences, and I think, Maulik, are you now ready to tell us about Oppenheimer's real work, namely his work on gravitational collapse? So over to you.
Thank you, Paul, for that introduction, and welcome everyone to the first talk of our new Thinking Beyond series. So I'm going to try to share my screen. This is always a moment of great apprehension. Let's see. Right, that work? Is this visible? Okay, so this is J. Robert Oppenheimer. The J, he insisted, didn't stand for anything at all. It was just J. Oppenheimer grew up in Manhattan. He lived on Riverside Drive, if you know where that is. And his father worked in men's suitings, and his mother was a painter. They both came from fairly modest backgrounds, but somehow or other, they managed to acquire great wealth. And his mother in particular, she was a painter, had a real eye for art, and she was able to sort of identify up-and-coming artists and buy their works and collect their works before they became outrageously expensive. And as a result, Oppenheimer grew up in an apartment where on the walls there were paintings by Picasso, Rembrandt, Renoir, Cézanne, and Vincent van Gogh. So that's the kind of life he had, absolutely amazing. And these and other stories about Oppenheimer's life are to be found in this 700-page Pulitzer Prize-winning biography on which the movie is based. But that's not what I want to tell you about today. I want to tell you instead about Oppenheimer, the physicist, about his science. So what did he work on? What was he known for? What did he discover? So Oppenheimer had perhaps 4 greatest hits, and here they are. They all have his name as well as the names of the people who were his research collaborators. I'll just briefly tell you about those. Born Oppenheimer Max Born was his PhD advisor at Cambridge, not at in Germany. And he and Oppenheimer developed a technique that greatly simplified the process of predicting the chemical properties of molecules. It's a technique that's still used in quantum chemistry today, but it's not exactly a discovery. Now, the other three collaborators here, Melba Phillips, George Volkoff, and Hartland Snyder, were all Oppenheimer's students. Oppenheimer was very generous with the students. He would often give them some of the greatest problems that he was working on, thereby giving them a shot at immortality. So with Melba Phillips, he found an effect, he made a discovery about nuclear reactions. But the two things that I really want to tell you about today are these second two papers, the last two papers with George Volkoff and Hartland Snyder. And those have to do with the life and death of stars. Okay. So in talking about the physics of Oppenheimer, I thought I'd tell you a story. And it's actually a mystery story. And the mystery is the mystery of the stability of stars. So we're going to build our way up to a puzzle about why it is that stars can be stable. And Oppenheimer's own contributions are only going to come in towards the end. All right. So let's start with the familiar. Okay. We're surrounded by air, but the air is part of our atmosphere, and the atmosphere goes up maybe around 100 kilometers. So even though it's just air, all that weight of all those nitrogen and oxygen molecules is pressing down on us and exerting a kind of pressure that's known as atmospheric pressure. Okay, so the weight of all that air is always pressing down on us. Okay, so how much is it? Well, this atmospheric pressure is about 1 kilogram per square centimeter, which is about 15 pounds per square inch. So you might wonder, well, why is it that we don't feel it? Why don't we feel that there's a 15-pound dumbbell on every square inch of us? And the answer is that our bodies also contain air, and that air is at the same pressure. And because of that, it balances the external pressure, and there's no net pressure at all. So we don't feel anything. Sometimes we do feel it when, for example, if we suddenly change our altitude, our ears pop, and that's just the internal and external pressure equalizing. If you were, for example, to go into space without a spacesuit, which I don't recommend in general, then one of the many terrible things that would happen to you is that since there would now be no external pressure, the internal pressure would cause your body to expand. And basically, you'll balloon up to about twice your size. You won't explode because your skin is elastic enough to contain you. But you'll sort of blow up because of that internal air pressure. Okay. Now, what happens though if you increase the pressure? For example, you could go underwater. Well, we saw this recently. If you go far underwater, then the pressure greatly increases. This is the unfortunate Titan submersible. And so if you're far underwater, let's say at the depth that this submersible was, the atmosphere, the pressure is about 400 atmospheres. And so that's not like a 15-pound dumbbell on you. It's more like an elephant on every square inch. And if there happens to be a design flaw, like there was here, then all that pressure will cause the hull to collapse, as you can see in this simulation. So this all happened within a span of milliseconds. Okay. All right. So the takeaways so far are one, there's gravitational pressure from the weight of everything above you. And two, if the pressure isn't balanced, it can cause an implosion. Okay, so those are the 2 points from this familiar real world sort of effects. Okay, well, that raises an interesting question and a puzzle that occupied many of the physicists of the 1930s. What prevents a star from collapsing under its own weight? I mean, the sun, for example, is 1,000,000 times the mass of the Earth. And so there's all that weight of the sun. And so what prevents the inside of the sun, for example, which bears the weight of all the exterior of the sun, what prevents it from just collapsing under all that gravitational pressure? So this was the sort of big issue of the time in the 1930s. And well, one way to, as we've seen, to prevent the collapse is to have pressure of your own. If you balance the pressure, as we saw with our own bodies, then you could prevent the star from collapsing. So what could give the star some pressure of its own to counteract the gravitational pressure from all that weight? Well, one way to create a lot of pressure is to have temperature. If something is very hot, that means that the particles are all agitated and they're moving about very rapidly. And as they're moving about, they sort of exert a pressure. And that pressure can, if it's hot enough, can balance the pressure of the gravitational collapse. So if you calculated the pressure from the weight of the sun is in the millions of degrees, right? So it kind of looks like this. The sun has different layers. The outside, which has a pleasing yellow light, is at about 6,000 degrees or so Kelvin, which is the same as Celsius, pretty much. And inside, though, it's about 15 million degrees. Okay, so how do you get to 15 million degrees? Well, you have to burn something, but this is no ordinary fire. At those kinds of temperatures, ordinary matter as we know it doesn't exist. Solids would melt at those temperatures. In fact, and liquids would boil off, and even gas doesn't exist. We have a new fourth phase of matter called plasma, and in that phase, the electrons are stripped off away from the atoms, and there's just the nuclei and the electrons separately. So so the sun, our sun, for example, is a ball of plasma. So we have this hot ball of plasma, and one question is, well, how did it get so hot? And so it has to be burning something, but the way it burns something is not through a fire. This is no ordinary fire at millions of degrees. It's a thermonuclear fire. It's a nuclear fire. So what that means is the sun bombards different, basically different atoms of different nuclei of hydrogen collide with each other, and they fuse, and they form other elements, other chemical elements like helium and carbon and nitrogen and oxygen. And basically, each time they do that, they release some energy, and that's what keeps this whole process going. So the sun is literally a factory for making, it starts out just as a ball of hydrogen, but then it makes all these other elements. And it's an amazing fact that every single atom in us, every single one except hydrogen, was once inside a star. So we're really literally made of material that was in stars. Okay, so that's what keeps this whole thing from collapsing. The sun has this thermonuclear fusion going, and that is what creates enough pressure to counteract its own weight. All right, but there's a problem. The problem is what happens when the star has run out of fuel. After all, it's transmuting hydrogen to helium and so on, but it only has a finite fixed amount of these fuels. So what happens when it starts running out? In the case of our sun, this will happen in about maybe 5 billion years or so. So nothing to be afraid of for now. But eventually it'll happen. And the question is, well, what happens when the star runs out of fuel? If it has nothing to use in these nuclear reactions, it's going to be its temperature is going to drop, and it won't be able to generate the kind of pressure that it needs to counteract the gravitational pressure. But gravity will still be there, and so gravity will want it to continue to collapse, and how is the poor dying star now supposed to oppose that? So that was the state of affairs in the 1930s. People were wondering what would happen to stars as they started running out of fuel. And an important part of the answer to that was provided by a young Indian physicist called Subramanian Chandrasekhar. And here I want to say something personal. When I was a kid, my father took me to a public lecture by Chandrasekhar, who was then, I think, almost 80. And I remember that Chandrasekhar's talk was about black holes. And I also remember that I didn't understand a word of what he said. But it must have left an impression on me, because now black holes are a big part of my research. Anyway, at the time of the story, which was in the which was around 1930, Chandrasekhar had just graduated with a degree in physics. He was at the age of 19, and he had just been admitted to Cambridge University to continue in England to continue his to get a PhD. Now, this is 1930, so there was no British Airways, and Chandrasekhar had to go by sea, which meant being stuck on a ship for 18 days with no Wi-Fi. So what did Chandrasekhar do? Well, he spent the time, like any 19-year-old would, using the newly discovered laws of quantum mechanics to solve the mystery of the stability of stars. So that's what he did. And what he found was this: when you try to cram certain kinds of particles called fermions, when you try to cram these fermions on top of each other, they hate it, okay? And they respond by resisting the compression with a pressure of their own. And that pressure is called degeneracy pressure. And the interesting thing about this degeneracy pressure is that it doesn't involve burning anything or using up any fuel. It's just always there. It can't run out. So there is the explanation. Once the star collapses to a certain size, the electrons are all on top of each other, and they respond with electron degeneracy pressure, which permanently halts the contraction. Except that when Chandrasekhar tried to see how the math would balance out, he found that it only works if the star's mass was less than 1.4 times that of the sun. So for stars that are less than this limit, now it's called known as the Chandrasekhar limit after him. That's they're going to forever be so-called white dwarf stars, which are supported by electron degeneracy pressure, and don't collapse anymore. So their weight is supported by this new kind of pressure. But that, of course, leads to our next question. There's a limit. So what happens if the star is heavier than 1.4 times the sun? Now the electron degeneracy pressure isn't enough to block the gravitational pressure. So there's nothing it's not strong enough to counteract the pressure of all that weight. So that's where the mystery is right now. And this is where Oppenheimer comes in. So when electron degeneracy fails to halt the star's collapse, the electrons get crammed on top of each other, and something amazing happens. So in atomic physics, we have electrons, we have protons, and we have neutrons, and those are just three different kinds of particles. But when they're all on top of each other, the electrons merge with the protons to form neutrons in a process called inverse beta decay. It's completely crazy. I mean, these are different species of particles, right? It's like a ostrich and a deer deciding to merge and form a giraffe or something. But that's what they do. The electrons and the protons merge, and out come more, and they turn into neutrons. And the neutrons then exert their own degeneracy pressure to halt the implosion. Oppenheimer and Volkov then calculated how much degeneracy pressure the neutrons could exert, and they found that they could resist collapse for stars that were less than 2.2 times the mass of the sun. Okay? So stars lighter than this Oppenheimer-Volkoff limit of 2.2 times the mass of the sun, they can live forever because they're not burning anything anymore. They're stabilizing themselves with this new kind of pressure. And they're called neutron stars. And neutron stars are absolutely amazing. They're the densest material that we know of. A single teaspoon of neutron star material weighs about 1 billion tons, as much as Mount Everest. And we've seen lots of neutron stars already. They often are spinning, and if they're spinning, they emit a kind of light, a beam that every time it flashes, it looks like a spotlight, and every time it flashes past us, we see a little pulsing light. So we call them pulsars. And here is a picture of the Vela pulsar, one of the neutron stars that we've observed. Okay. All right, but back to our puzzle. Well, I know what you're thinking. The Oppenheimer-Volkoff limit says that stars up to 2.2 times the mass of the sun are safe from further gravitational collapse because of neutron degeneracy. But what happens if the star is heavier than 2.2 times the sun? So this was the state of affairs, and now we have a further problem. There are these stars that are even bigger than that, and they can't be stopped by burning. They can't be stopped by electron degeneracy pressure, and they can't be stopped by neutron degeneracy pressure. So what happens to those? And now we come to Oppenheimer's greatest result, in my opinion. With his student Hartland Snyder, Oppenheimer and Snyder decided to confront the collapse question head-on. You see, in Einstein's theory of gravity, in his general theory of relativity, space and time are not fixed. They are flexible, and they respond to matter and energy by changing their shape. So space can actually change its shape. So what Oppenheimer and Snyder wanted to see was what happens to space and time when there's a collapsing star inside it. And so they set up their equations, and the equations are very complicated. So to deal with those complications, they made a few simplifying assumptions. For example, they assumed that the collapsing star was perfectly symmetric. A realistic star might not be perfectly symmetric, but they assume that, well, that's roughly what the star looks like. So when they plugged into their equations, they also considered two different perspectives. The perspective of someone falling in with the surface of the star. So the star is collapsing under its own weight. The space and time are reacting to this collapse. And observer number one is foolishly riding the surface of the collapsing star into wherever it's going, while observer number two is safely watching the collapse happen from outside. Okay, so Oppenheimer and Snyder considered both these perspectives. And what they found was absolutely mind-blowing. They found that the falling observer, along with the collapsing star, is crushed, no surprise there, and obliterated within about a day. So when I say obliterated, I mean really obliterated, gone, like disappeared from space and time. So this was kind of shocking. It's not just that they're there crushed to a little lump. Both the observer and the collapsing star simply disappear, and this happens in about a day. The second viewpoint was from the outside observer's point of view, and the outside observer sees something just as bizarre. He sees the star surface rapidly shrink, but then suddenly slow down as it approaches a certain critical size. So the outside observer cannot see what happens as the star and the falling observer cross that critical radius. So if you're watching from outside, you see the star shrink and then just sort of slow down, and it doesn't shrink past that. Instead, as the star shrinks to this critical radius, it and the falling observer, which they see on the surface of this imploding star, simply fade to black. So here is what it looks like from outside. The massive star exhausts its nuclear fuel, which was previously preventing it from collapsing, and then the star implodes, and as that happens, it just sort of fades to black. So in particular, when the infalling observer has already gone into the past this critical radius, but the outside observer can't see them do that. They never see them disappear. It's as if time has come to a stop. So in modern language, what has happened is the star has formed a black hole. The critical radius is called the event horizon at the black hole, and beyond which you can't see. So it's almost as if the inside of the star has cut itself off from the rest of the universe, and the outside observer just can't see past this event horizon. And meanwhile, inside the black hole, the observer is crushed and removed from space and time at a place called the singularity, where they experience a very painful death. So this was the result of Oppenheimer and Snyder. Oppenheimer and Snyder predicted that black holes would form through stellar collapse. Okay, so the whole idea of black holes existed already before, but nobody really knew how. They were just mathematical oddities, and nobody really knew whether they existed. Oppenheimer and Snyder said, not only do they exist, but they're inevitable. They're going to be created by very heavy stars collapsing under their own weight. So Oppenheimer and Snyder were very excited about their discovery. They wrote up their paper and they sent it for publication, where it appeared in the top physics journal called Physical Review in volume 56 on September 1, 1939. I think on page 455. Unfortunately for Oppenheimer and Snyder, September 1, 1939 was not a good day to publish their work, because that was the day that Hitler invaded Germany, invaded Poland rather. The German army rolled into, the German tanks rolled into Poland, and of course, this became the biggest news of the day. And the whole world was preoccupied with this. So, and Oppenheimer and Snyder's work was essentially forgotten. In fact, it was even worse than that. Their paper wasn't even the biggest physics news of the day. In the same journal, Physical Review, on the same issue that appeared on September 1, 1939, just 29 pages earlier was a paper by Niels Bohr and John Archibald Wheeler, which outlined the mechanism of nuclear fission, and in particular identified that the element that would permit nuclear fission, that would be best to use in nuclear fission, was uranium. So this was quite an extraordinary day. You had World War I starting. You had a paper that was instrumental in creating the bomb that would end World War II, and you had the prediction of the existence of black holes. So Oppenheimer and Snyder's work was ignored. Well, and then what happened after the war? Did they get their due? And the answer is no, they didn't. After the war, Oppenheimer was distracted. Of course, his legacy had become that he was the father of the atomic bomb. On top of that, he was soon fighting charges that he had been a communist sympathizer and potentially a traitor. Meanwhile, the whole idea of a black hole was a step too far even for theoretical physicists. I mean, theoretical physicists are an imaginative bunch, but what Oppenheimer and Snyder were predicting was that inside the black hole, the laws of physics would come to a halt. Outside the black hole, the time would essentially come to a standstill, and whatever it was, and the inside and the outside of the black hole would be cut off. So it's as if a region of space and time had simply cut itself off from the universe. That was all too much for physicists, even physicists, to handle. And there was massive resistance to this idea. Einstein in particular was appalled by black holes and said black holes do not exist in physical reality. Wheeler says there should be a law of nature to prevent a star from behaving this absurd way. So physicists were not ready to accept black holes, and more specifically, they criticized Oppenheimer and Snyder by saying, well, you know, the problem that you looked at with this idealized, perfectly spherical star, that's just not realistic. No star is perfectly symmetric like that, and so maybe you only found this mathematical solution because of this highly idealized case that you studied. This is actually something that happens in physics sometimes, where there are these mathematical solutions that exist as idealizations. For example, there could be wormholes or time machines or maybe passages to another universe. And all of these, they're actually there in the math, but they're very delicate. As the slightest perturbation from some perfect system, and the whole thing capsizes and disappears. So, you know, you could have a little mouse sneeze on the other side of the universe, and suddenly white hole or wormhole or time machine will just fail to be a solution anymore. It will just disappear. And the thinking was that maybe black holes, maybe Oppenheimer and Snyder's picture was similar to that. Today, of course, the issue was finally settled in 1965 when a British mathematical physicist named Roger Penrose proved that no matter what, black holes are inevitable. And Penrose didn't assume anything about the kinds of, he had a very general mathematical result. And finally, in 2020, Penrose received the Nobel Prize for Physics. And I tend to think that if Oppenheimer were alive in 2020, then it might have been possible that he might have shared the prize with Roger Penrose. Okay, well, today we know very much that black holes are real. Here is an actual photograph taken by the Event Horizon Telescope of a black hole surrounded by a glowing halo of plasma. Okay, it looks a bit like the Eye of Sauron. We might even have seen black holes being formed out of stellar collapse. And here's a video from NASA about that.
For the first time ever, astronomers might have witnessed a star actually become a black hole right before our eyes, or telescopes. In this visible light image from the Hubble Space Telescope, we can see a large star about 25 times the mass of our sun, around 22 million light years away in the galaxy NGC 6946. This was in 2007, but in a Hubble image from 2015, looking with the same filters at the same wavelengths, the star appears to be gone. One possible explanation, the star died and became a black hole.
So there might be some other more prosaic explanations, but that's, I think, a very nice, compelling observation. So I think that, well, let me end by with some general remarks. I think if you think about what's a unifying theme that runs through Oppenheimer's work, you know, he worked on the bomb, on black holes, on stars.
For the first,
it's probably Einstein's famous equation, E equals mc squared. So this equation says, in this equation, we have E, which stands for energy, M, that stands for mass, and C is the speed of light. Now, the speed of light is, in ordinary terms, is an enormous number. It's the speed of light is about 300,000 kilometers per second. So when you square that, as you see in this equation, you get an even bigger number. Okay, it's actually 300 million meters per second, and you square that. And so this equation says that energy and mass can be traded. You can take a little bit of mass and destroy it and get energy. And how much energy you get is obtained by taking that mass and multiplying it by this enormous number c squared. So even a tiny amount of mass will liberate an enormous amount of energy. And it's an absolutely amazing fact that in the Hiroshima bomb, which obliterated, an entire city, only less than 1 gram of matter was turned into energy. And that was in the Hiroshima bomb. We have got more powerful bombs since then, more destructive weapons. Here is a video. Oops. Hold on. Sorry. Let me go back here. This is a video of. Sorry. Yeah, this is a video from taken that was recently. This is a video taken of the Tsar bomba, which is the most powerful nuclear weapon ever exploded. It was a Soviet device, a hydrogen bomb of the kind that Edward Teller is in favor of making in the movie Oppenheimer. And this was the footage of the explosion of that hydrogen bomb, as taken by the pilot who dropped it, the Soviet pilot who dropped it. And this footage was actually classified and has only recently been declassified. And here it is. So the bomb is on a parachute to give the pilot time to escape.
Экипаж одевает защитные очки.
Yeah, like God.
Приближается к точке взрыва. Высота 4000 метров. Осталось 3 секунды. 2, 1, 0. Взрыв сопровождался световой вспышкой необычной силы. В этот момент самолет-носитель находился в 40 и последующие свечения, несмотря на сплошную облачность, были видны в радиусе до того, прямой столб, поднимающийся с земли, быстро увеличился в объеме. Через несколько секунд после взрыва диаметр пулевого столба составлял около 10 километров. Увеличиваясь в размерах, облако медленно поднималось вверх.
This is a view from about 100 miles away.
Оно достигло высоты 60-65 километров.
This is pretty horrible, but this weapon, which was, as I said, the most powerful weapon ever used, it only changed 2.4 kilograms of matter into energy. So that might make us feel powerful, but here's a little bit of context. So as I said, the Hiroshima bomb was less than a gram. It was only about 700 milligrams of matter was turned into energy. The Sara bomb, the hydrogen bomb, was about 2.4 kilograms. And just to compare that with what happens in nature, our sun, in order to prevent its in order to resist its collapse, is going through these hydrogen bomb type thermonuclear reactions all the time. And every second for 10 billion years, our sun destroys 4 million tons of matter. And it's ironic that this very thing that we used for destruction is actually producing the sunlight, without which we wouldn't be able to live. And finally, the most energetic thing that we've ever seen is two black holes merging. And when two black holes merge, the resulting black hole often has less mass than the two black holes that formed it, and so that difference in that mass is turned into energy. So in the case of in 2015, we for the first time saw two black holes merging, and in the process they converted about 3 solar masses into energy, which is 6 billion tons. So that's very humbling. And on the same note, I'm going to end here by putting up one of Oppenheimer's favorite quotes. This is from the Bhagavad Gita. Thanks for listening.
Thank you, Maulik. That was entertaining and sobering together. We've got a lot of questions. I've got a couple of things that occurred to me as you were speaking. I thought, well, Chandrasekhar must have known Oppenheimer well, but didn't seem to feature in the Manhattan Project. So I quickly checked, and it turned out that Chandrasekhar spent the war years working on ballistics, not on the Manhattan Project. Oppenheimer wanted him for the Manhattan Project, but familiar story, couldn't get security clearance. And I wonder whether he is recognized much, because he was born in Lahore, which is now Pakistan, but I think he went to school in what was Madras at the time.
Yes.
Is there much recognition in either India or Pakistan for Chandrasekhar's greatness?
Yes, in India for sure. He's considered an Indian physicist. Although he became a U.S. citizen and lived most of his life in Chicago,
Right.
He also maintained ties with India and frequently came back there.
Right. And
of course, his great discovery, for which he won the Nobel Prize 50 years later, was as a 19-year-old who had just been trained in India. Well, basically self-taught.
Yes. Well, let that be an inspiration to any students who are watching us now. You can do Nobel Prize winning work even at the age of 19. So that's a wonderful thing. When you showed that film of the hydrogen bomb, of course, in the film, that is in the movie Oppenheimer, you may remember that it's referred to as the super. So Edward Teller didn't want to mess around with footling little fission bombs, wanted to go straight for the fusion bombs called the super at the time, and then subsequently became called the H-bomb. And he got a sort of rather bad press for his gung-ho attitude to nuclear weapons. And when I saw him, he was towards the end of his life. We had lunch together in Italy at some conference. He'd just come from Moscow, where there was a conference on the possible uses of nuclear weapons to deflect killer asteroids that, if they hit the Earth, would cause immense destruction. So perhaps there's a positive side to nuclear weapons after all, to nudge the killer asteroids aside. But enough from me, because we do have quite a lot of questions in the queue. And I'm going to just take them in the order that I see them here. So Nitin Mishra asks that the conclusions, the Oppenheimer-Snyder paper, what led to their conclusions about black hole formations? Was this the equations themselves, or a hypothesis by Oppenheimer and Snyder? And I think actually you covered that, because you made the point that the equations they were using were Einstein's gravitational field equations, so they tell you about the collapse, but they have made the simplifying assumption that it was an idealized sphere. And so at the time, it could easily be dismissed as just a sort of mathematical idealization. But Penrose subsequently showed that you can't avoid the collapse of a black hole by relaxing those restrictions.
Yeah, of course, they were doing all their calculations by hand. There were no computers or calculators in those days. So they had to simplify the problem. They couldn't do any computer simulations or the kinds of things that we can do now. We have now looked at computer simulations where the collapsing star is not taken to be spherically symmetric at all. And Oppenheimer's intuition that that it doesn't really matter if it's symmetrical or not, it's going to collapse anyway, turns out to be correct. So if you change its shape a little bit, so it's no longer spherically symmetric, it still collapses into a black hole.
The other thing that you mentioned, that touches on one of the questions that I answered earlier just by email, is that a lot of this wartime work on the Manhattan Project, the people they were recruiting were interested in astrophysics. And a lot of the nuclear physics that we now apply to stars was really worked out during those war years as a sort of byproduct, and including the formation of the elements. So one of the questions was about, are we really made of stardust? The carbon in our bodies was manufactured in the cores of long dead stars that exploded and spewed this material around. And that was all worked out. Ironically, that was by Fred Hoyle, who during the war years didn't work on the Manhattan Project, but on radar in Britain. And he collaborated with Willie Fowler at Caltech to work out all those details of nuclear physics. So it's an astonishing thing that in the 1930s, it was a bit of a mystery as to what made the sun shine and what went on inside stars. And by the end of the war years, that had been pretty much put together.
Yeah, they didn't know. They didn't. They had no idea how long stars lived or how they worked, basically, and they figured it all out.
Right.
One clue was the Earth, actually. The fact that they knew from geological evidence that the Earth was more than 1 billion years old, and their earlier calculations of how to keep the star from collapsing only allowed it to last for about 30 million years. So they didn't know whether stars lived millions of years or billions of years. But the fact that the Earth was so old suggested that the stars should be at least that old. And that to them was an indication that there was something else going on. And that was, of course, nuclear reactions.
So now,
I also want to say one thing about this Oppenheimer-Snyder work. It turns out that there was a paper by an Indian physicist called Vishveshwar Dutt, which was 2 years earlier, and which had exactly the same equations. So I looked at that because there was, people claiming that it really should be credited to him. Vishveshwar Dutt made had some real misfortune. First of all, he decided to publish his paper in German. So he wrongly guessed, which country would be on top after the war, I guess. So he decided to have his article translated to German and published in a German journal. So that didn't help it with its visibility. But in addition, he himself died of a simple botched hernia operation a few years later. But he did come up with the equations. But then I looked at the paper, and it's clear that he didn't understand what he was doing. That he had solved the right equations, but almost by chance. And he even says this has no physical significance and is not clear, and it's just a mathematical game. I think we can give him some partial credit, but it's clear that Oppenheimer and Snyder knew what they were doing.
Well, that's a fascinating story. I knew nothing about this unknown individual. So our old friend Barbara Temple has sent us a few questions. And one of the things which is going off in a different direction is that Oppenheimer, famously quotes the Bhagavad Gita, and he learned Sanskrit and so on, and clearly had an interest in Eastern philosophy. But actually, at that time, this was rather fashionable because Niels Bohr did as well. And Barbara is asking, well, why is it this preoccupation with Eastern philosophy? And my answer to that is because in quantum mechanics, which they were all preoccupied with, the relationship between the whole and its parts is very unlike the sort of traditional reductionist, materialist Western view of the world, that you chop things up and there are little bits inside them. It's a more subtle arrangement that was understood in the 30s, but became more fashionable in the 1980s. with the rise of sort of California holistic thinking. But it was certainly all there, I think, in the 30s. So I don't know if you have a different slant on that.
Yeah, and also the idea that the observer determines reality in a way, and there's a sort of concept of illusion, and at least in Hindu philosophy, there's something called Maya, which just means the world is not as it seems. That said, I always find that this is really a stretch. That you really want to connect the dots here and try to relate science to religion. And a colleague of former colleague Brian Greene, the straight physicist, once had the opportunity to talk to the Dalai Lama, and he asked him very openly, he says, is there really a connection between modern theoretical physics and ideas in Buddhism? And the Dalai Lama, to his great credit, answered very honestly, and he said, no.
Oh, really? Is that so? I did a couple of events myself with the Dalai Lama, and one of these, he spoke, maybe both of them, he spoke in Tibetan, and it was translated by his colleague who had a PhD in philosophy from Cambridge, and I often wondered whether we were really getting the Dalai Lama's own words or just the philosophical spin from the translator. But anyway, we should just move on because we've got some other questions here. So Barbara also asked, well, is it true that when you fall into a black hole or an object falls into a black hole, it looks redder and dimmer to outside observers? Well, I think the answer to that is yes. We probably move on. And then we have from an anonymous attendee, in the film Oppenheimer, it's mentioned that there's a chance of an atomic bomb causing the atmosphere to ignite. Is this true, and had it been researched more? And I think that it was certainly the case that this possibility was raised, but I think they rather overdid it in the film, because I think in practice it was just one night of panic whilst people worked out the equations. I don't think it was a sort of extended worry. Is that your understanding, Maulik?
I'm actually not sure what effect they were.
Yeah. It certainly is a real incident, but I think it was just somebody being a bit difficult. Then Kalyan Patak, is there a geometrical equation corresponding to Oppenheimer and Snyder's work, as E equals mc squared is related to the Pythagorean theorem? Not sure about the answer to that one.
Well, yeah, in a way. So it's actually the way to think about it is more through Roger Penrose's work, which says essentially that because gravity is attractive, the geometries are always such that things converge, and so the matter that's originally part of the star converges to the singularity at the center. And there's a kind of inevitability of it that comes about from the general attractiveness of gravity, the fact that it's attractive and not repulsive.
Okay, we've got time for only a couple of questions, which I know we can answer quickly. One of these is from Gormagarayan. I have to apologize if I'm not pronouncing people's names correctly. If we can turn matter into energy, can we turn energy into matter? And yes, you can. What a better example than the Large Hadron Collider, where the kinetic energy of counter-rotating protons that smash into each other produces whole showers of new.
So, but you know that
particles.
Einstein actually never wrote down E equals mc squared. He flipped the equation and wrote m equals E over c squared. And it's the same equation, just algebraically transformed a little bit. But the emphasis is very different. E equals mc squared is an equation that emphasizes destruction, about how you can destroy matter and turn into energy. But Einstein was more interested in creation and how we could create matter out of pure energy. So, yes, very much so. We can turn energy into matter, and it's quite possible that all matter was originally energy.
Final question from Fletcher Griffin, who asks, so black holes form from the collapse of stars, and do black holes themselves somehow vanish? He says collapse. Well, they do vanish, but only over a long period of time. By the Hawking process, the quantum effects of black holes cause them to glow with heat radiation, and they evaporate away over an immense period of time. So they do end up vanishing as well, although quite what the final little speck might be is still not decided. It's very much a subject of active investigation, including at Arizona State University, I might say.
Yes.
I think we probably have run out of time. So
I'm happy to stay and answer questions if people want
we could stay on for a little bit. For those people who don't want to stay, I would just like to remind them that they should join us in September, the last Monday in September, for something completely different, which will be the topic is biomagnetism, and so people should feel free to go. But we could stay for just a few more minutes and take some of these further questions. I'm scrolling up.
Maybe we can just answer them in order.
Yes, except
Jason Gale asks, we've discovered there are numerous black holes throughout the universe. Why haven't we discovered any white holes? That's a great question. And maybe white holes are a solution of Einstein's equations. Einstein's equations allow for something completely the opposite of black holes, they're the opposite of, so a black hole is like a Hotel California, right? You can go enter, but you can never leave. And the white hole would be the opposite. You can never enter and things just keep coming out of it. So that's equally ridiculous. And maybe there's even some sense in which black holes and white holes are connected. Maybe, flush something down a black hole and it comes out through a white hole somewhere else. But most probably they don't exist. And that's because they are very special. They're unlike these theorems about black holes that form under very broad circumstances. There's no real way to create a white hole. But who knows?
So do we want to move on down and just take a couple more? For an observer far away from the star, how long does it take for the star to collapse into a black hole?
Oh, this is fantastic. It never collapses into a black hole. That's the amazing thing. Time comes to a complete, for an observer from outside, time comes to a complete stop. And so the observer outside never actually sees a black hole ever form. The inside person's black hole's already formed, the one inside is already dead, but the outside one never sees it happen. And so it's really... It
does, however, the collapsing object goes dark, as you showed in your picture. And Barbara was asking about the reddening effect, and that's true. It's very rapid. The imploding object gets redder and redder, and this is all on a time scale of a fraction of a second. And so once the wavelength of the light gets very long, it's effectively a black object. But if you could sort of somehow deduce where is it now in your frame of reference, it would never cross the event horizon. Quite different if you're on the star going down in the collapse, then of course it all happens very quickly and you do cross the event horizon.
Yeah.
We've got another question. When we say black holes are inevitable, does that mean most large stars are likely to become black holes?
I think the answer is yes.
Right. I'm old enough to have been working in this area before the first black hole was discovered. The first candidate was discovered, and it seemed at the time that it was entirely likely that they either don't exist, or if they existed, they would be extremely rare. And one of the astonishing things during my career is that now it seems black holes are a very common component throughout the galaxy and throughout the universe. It does seem that they form under a wide range of circumstances, not just stellar mass black holes, but the supermassive black holes at the centers of galaxies, which is still something of a mystery. And the James Webb Space Telescope is peering back to the very earliest stages after the Big Bang. And one of the mysteries seems to be, how do these monster black holes form in such a short period of time? Do you have an opinion on that, Maulik?
about how these black holes, these very
Yeah,
large.
the supermassive black holes at the centers of galaxies that seem to have been around in the universe very early on. The mechanism whereby they form, I think, is still
right.
Keeping people
also,
guessing.
Yeah, I think there's still debate about that. There's, I think that one of the candidates' theories is that black holes in those early black holes just kept merging with each other and forming ever bigger black holes. So that might be one way to, or you know, galaxies collide with each other, and so our own galaxy, the Milky Way, is going to collide with the Andromeda galaxy in a billion or so years. And when they do that, the black holes at their centers can also collide with each other and merge. And that's one way for them to get bigger.
I think we'll have one final question and then call it a day. This is Howard Lannis, who asks, why are our nuclear reactions so inefficient in comparison? I guess in comparison with the bomb movie you were showing. Is that because they're fission rather than fusion? And well, the answer is yes. A nuclear reactor like the one at Palo Verde in Arizona, these are fission reactors. You've still got a lot of power, but they are based on fission. The idea of controlled nuclear fusion is what the sun is doing. It's what the hydrogen bomb is doing. But can you control that in the lab? That has been a quest which extends back. I almost did my PhD back in the 1960s on controlled nuclear fusion. I'm pleased I didn't, because all these decades later, they still haven't quite pulled it off, although there are research groups around the world. They keep saying, well, they're getting very close, and in another 15 years, they should have an industrial controlled nuclear fusion device, and they've been saying 15 years for my entire career. So
yeah, but you know, the hottest place in the solar system, the hottest place in the solar system is not the center of the sun. For a while, it was Princeton, New Jersey, where inside a nuclear reactor, we temporarily could make a plasma much hotter than the center of the sun. That reactor has now been shut down, and there are other reactors that have since broken that record. But
yes, you have to make it hotter than the sun, because you don't get very long for the fusion process to occur. The sun can just sit there and do it very slowly. It has a lot of material, so it just doesn't need to gobble it up quickly. But if you want to make a commercial reactor, you need to have something quick. Well, I think that's all, and let me thank you, Maulik, for that very entertaining and informative presentation, and thank our audience, and hope that you will stick with us and come back each month, because we have a very varied program ahead of us. So it just remains for me to wish everybody good night, and to thank Jessica for steering this successfully. Goodbye, everybody.
Bye-bye.